if it is about technicalities, I add to it the next sentence, but every single value I've learned from Peter.
Yankee, are we supposed to read that?
You know, don't. The rest, yes. Okay. Few pictures, I guess, 3 circles of families, starting with very young Peter, somewhat older, still very young Peter, but in the second circle, and then the third circle, which is academic. So David Blackwell and Eric Lehman, and the younger generation, which I just pick. Random pictures that I had in monochrome, so it was simpler to put. Anyhow, so this is the background. Few things about this talk, which is too small probably to read, and this is a problem. And the subject of the talk would be statistical testing. It is a historical account, so it's not a research paper. Historical account of a work done during 60 years from his PhD to unpublished recent paper. The common theme is non-parametric assumptions, at least under the alternatives. Saying history about Peter is slightly understatement because Peter is making history, so we have to take this in mind. I was surprised to the level of uniformity that I found in these papers. The sequence would be chronological, but there is almost no order. I want to make a point that this is not a history of testing, nor it is intellectual history of Peter, but a small intersection of the two, that is Peter and testing, which is not a main topic for Peter. And the main, in a nutshell, what I see is this basic tension that we have, and I guess Peter has, that testing is in many fields. For example, in the field that brought Peter to statistics, psychology, testing is much more important than estimation, strictly more important. For example, because what is now is called transfer learning. So if you do experimental psychology, your issue is transfer learning. And estimation doesn't transfer easily. Testing, much more easier, and therefore the focus should be on testing, because testing can be generalized. Estimation values are not generalized. They are a function of the first year students, which used to be the research sample in the history, or the Turks of Amazon. Currently, they are not the general population. So making estimation is not something that makes any sense. Moreover, everything is in the context of experiment, and nobody cares about this particular manipulation. We want to generalize, and this is testing. However, we are used to think about optimality. That is what we are trying to do, optimality, minimax, efficiency, and we don't have a notion or a concept of optimality in testing. The talk would be, as I see it, in a C minor. It will be relatively undertoned. I leave, I guess, the D major finale with crescendo and tutti and all this to the last talk, which probably will be delivered. Okay, but I'm supposed to celebrate, so there would be some music. And So I try to look on the work of Peter on the 60 years of work. And this is a list of his most cited paper. No, it didn't say. This is the most cited paper outside statistics. So I didn't see much, so I looked by year. And this is the most cited paper by year. What you hear in the background is a concerto for something and orchestra. What is a something? So the young generation doesn't, couldn't. Which instrument is it? Typewriter. Okay, there would be more. So let's start with a little known paper of Peter from 2000 called Non Semi-Parametric Statistics, Compared and Contrasted, which tries to understand or to make a point what is non-parametric and what is not, and in particular that the word non-parametric is used in two orthogonal ways in statistics. So there are two types of non-parametric statistics. One of them is the older version, which is dealing with things what is usually called now non-parametric statistics. I think the sense of non-parametric statistics that would be used in at least one of the afternoon talks is something that is connected with density estimation, regression, non-parametric, so-called non-parametric regression. The main point that this procedure were developed not so far with notions of asymptotics, distribution, inference, etc., but based something like consistency, no confidence, real confidence bounds and p-values. And the central point is a sentence in blue that says for VJ, however, practically speaking, the techniques are mainly used as exploratory tools and compared by their visual effects, visual results. These were not Peter's words. It means that he sees them for the first time today. I'm not sure he saw them before. What?
I don't even remember the other.
You wrote the red sentence. In the red sentence say, asymptotic approximation were developed, but the criteria of optimality such as integrated mean square error were and are not driving force. Rather, the development of interesting, pretty pictures for exploratory analysis is paramount. And the editor didn't agree to publish this sentence. Yeah. So this sentence was supposed to be changed, and it was changed to the blue.
What journal was that?
Statistical, what is this? No,
Science.
inference and
Oh, planning SP. Planning.
yeah, and the editor didn't agree officially because the referee didn't agree. I don't believe that there was a referee in the middle, but the compromise was a blue one, but Peter had nothing to do with this compromise. The older sense of non-parametric statistics is things like rank test, things where you want to guarantee p-values for non-parametric hypotheses. And the driving force of all this work was classical inference p-value testing. Here you have the notion of robustness, which is part of this package, and part of this trend of non-parametric statistics in the inference sense of the word, no pretty pictures. Semi-parametric is a sort of trying to look on non-parametric problems, but with strongly with emphasis on inference, square root of n rate, optimality. Bootstrap would appear, which is the main topic of Peter, is a combination of this concept of non-parametric. It started with non-parametric maximum likelihood estimator, with the idea of being able to plug in, and it is strongly related to a permutation test, of course, and the whole idea is to do inference. Okay. So we have to continue with music. And so again, trying to figure out what are the tokens. These are papers in logical order with a size proportional to citations. Thanks to the University of Michigan marching band. And, okay. The early stage local alternative, this is the PhD thesis or the paper, a paper based on the thesis. On some asymptotically non-parametric competitors of the Hotelling's T-square. So I'll be very fast. Many years ago, there was, I think it was a talk by Prokhorov in Berkeley, in the International Congress of Mathematicians, but it was one of the Russians, and the talk was given in Russian with the interpreter, and Peter described it as that the second slide was long with a lot of details. The speaker talked about it 10 minutes, and then the translator said, assumes it is Prokhorov. Mr. Prokhorov presented something that we all know, so we can move on. And that was the last slide I could follow. So the paper starts with basically a translation model, multivariate translation model. You have an estimator of theta. X is vector in RP. Theta is the location vector. It is based on basically vectorizing real estimators, invariant estimators. So you have typically the structure is something like H of the translation, which is mu n, let's say 0, but not necessarily, and which is the expectation, and you try to equate it. Symptotics is based that everything is under local alternative is Gaussian with shift, which is proportional to the alternative. So we are looking on local alternatives, which is the basic notion of all this work, which is theta n, now it's vector, is 1 over square root of n a. And we have both of the estimator, two types of asymptotics, which are strongly related. One of them, the distribution of H under the alternative. This estimator, this estimating equation, sorry, this is estimating equation, its behavior, or the estimator. Both of them are normal with shift. And we have two types of tests, which are strongly related. One of them is based on the estimator, and one of them on the estimating equation. And the tests are as can be expected. So everything is derived. There is example. We are speaking about the 60. So the mean, the Wilcoxon, based on Wilcoxon test, the median. And then we come to efficiency, because we are dealing with mathematical statistics. So there is a notion of Pitman efficiency, which was paramount in the work of testing of Peter in the early area, which says that you compare the sample size needed to achieve the same asymptotics. And we get a sort of results like that. We have, and the point is that the left-hand side and the right-hand side are typically different. And so everything is analyzed, and the conclusion is the following. And there are two conclusions. First is technical. Wilcoxon and the median-based test are more robust than something that is based on the mean. But to my talk, more important is an undeveloped statement And I say undeveloped because that's all is written about it. Section 4 also points up to the need of satisfactory criterion of what is meant by better independent of delta. What is meant by better? What is the better statistics? And the problem is that better statistics depends on the alternatives, and there are a lot of them. And that's the main problem of testing. That the best statistics is depending what you think about the alternatives, and this is wild forest. And therefore, we don't have a satisfactory notion of statistics. There is another sentence in the middle that says there will always exist a direction in which one does worse than in one dimension, whatever estimate one chooses. And necessarily, because we compare two things, one in which one does better. So directions are, the best statistics depend on the direction, and you don't know the direction. Not much later than that, we have an application, and this is a sort of typical. It is work done with a shell. Test for monotone failure rate based on normalized spacing. So the model is that we have a distribution with failure rate. And edge notes say f is exponential. So it's very, very much parametric. And H1 is, the failure rate is monotone. How? I don't know. And that's, again, the main problem. The alternative is non-parametric, completely almost completely non-parametric. Yeah, it's non-parametric, even not semi-parametric. So they started with a set of tests based on order statistics, which are just take the excess, look on the different, normalize them properly. And if it's exponential, this would be IID. So we look on the rank of them, the rank of the spacings, and under H naught, the spacings are exponential. And under H1, they are stochastically monotone decreasing. And therefore, it makes sense to look on tests which are, in some sense, monotone in the spacing. And the result of the paper says that all monotone tests are rank tests. If we want to be pure monotone, that we have to do rank test. All monotone tests are unbiased, that's expected. And one type of monotone test is one that look on the rankings, apply some function of it, weight it, and in particular, the motivation of the paper seems to be a test suggested by, say, so it's some of the I are I, and they say two things about it. The first thing is that it is not efficient, and here we can say because it's dominated by another test, which is always better. And here is again, I'm not going to enter into all the detail to leave enough time for music. And the main that then they try to analyze, and what they claim that any test of this sort, if x is exponential with mean 1 or with non-lambda, it doesn't matter because we can always say normalize, then the efficiency, all tests of this form are non-efficient. So that's the fact that it is sort of non-interesting results. So it's very strong results that they were able to prove, because if you look on alternatives, for any alternative, any direction, you always can improve it. But if you drop the assumption that you know the scale, then suddenly all the standard type of test, in particular the one with the optimal C and J, are efficient relative to other tests. But still, if you know, you think about every test would be efficient relative to a specific alternative. So this is in a paper, second part of the paper, now authors by Peter alone, say the classes are all statistics of this form, when you have to normalize because you don't know the scale, all linear function of the spacing, locally most powerful test based on the ranks, or in particular, specific way on the ranks. All of them are asymptotically equivalent to the most powerful test for a given direction. The problem is that you have to know the given direction. Similar problem is in the following shortly thereafter. No, it's more than 1 year, it's 10 years. It's looking on taking the work and suggest a test for how well a model fits the assumption, which is uniform variance and nonlinearity. I'll talk only on the variance part of the story. And so it is a basic linear model. The model that we consider is that the variance depends on the expected value, conditional expectation. So tau is the conditional expectation of y given x, the linear part of it. And we consider local alternatives, that is H naught is that sigma is 1, but it may departure proportional to theta in a direction A. For example, sigma can be e to the power of theta tau, which is the deviation idea. In this model, there was an estimator, there was a test, and that was proven under conditions somewhat difficult to make precise, which is very polite way. I would probably put it in a stronger way, statement. So a test was suggested, and we get our test statistics. So the first part of the paper is taking this test, suggested test, and making the condition precise and the proofs real. And then we move to generalize this guy. But now we need complicated conditions and we need long proofs. And the resulting tests are asymptotically unbiased. The power is independent of the method of estimating the parameters, which is again something that would appear again and again. There is explicit theorem for the efficiency or the relative efficiency of the test. We can choose B to make things robust, but if the error distribution is known as expected, it B, the functions that appear here is explicit. And now we are left, what is A? And different A's would give us different tests, which would be given, and we don't know A. That's the whole idea of our problem with testing, that we don't know the alternatives. We have a non-parametric alternatives, and a different alternative would give us a different test. Okay. One thing about the graphics, all the graphics except one was done by me. I use Google Scholar, except for one tiny point, which is the name of Tobias Ryden, which was chaotic completely, and he covered all the screen. I didn't touch anything. That is, everything is automatically, and it was, I know, few points that I would correct if I want, but I insisted of just taking the automatic results, not to enter into biases. Okay. So one thing that knowing Peter, I think was very important to him was co-authors. So this is a list of the co-authors. Peter worked with it, and do you imagine how long it is? How many co-authors? Give me a number. How many numbers would it be?
400.
Exactly. Look at the wall. Oh, the order, by the way, the order, the colors, everything is right. Cincinnati Pops with Japanese 105 millimeter guns. Military guns, not the ones that you have here after a touchdown. Omnidirectional test. Okay. So I'm looking now for 2000 paper by Ali Salia, Peter and Thomas Stoker. Goodness of fit test for kernel regression with applications to option implied volatilities. I don't think people care about the options part of it, but the rest, yes. So the issue is completely non-parametric with W in RP, V in RQ, Y real, and we look on the non-parametric expectation of Y given W and V, and the H note is that expectation of Y doesn't depend on V. So the idea of the paper is, in theory, very simple. Let's look on the non-parametric kernel estimator of the two expectations. The one, the expectation of Y given W and V, and the other one is given only W with H note that says that the two are equal, H1 that they are not equal. So we look on kernel estimators. We are looking in high dimension. Kernel estimators in high dimension is catastrophic. Here it is more because we have to compare, test. It's really nasty job. The assumptions are nasty. The kernel should have R, which is larger than 3p plus q, which are the dimensions we are talking about. 3/4 of the sum of the dimension, 0 moments. So it's non-standard estimator. We have to kill the bias. That's the main problem. Everything we try to look on the numbers, it's okay, it's not parametric. In the worst case scenario, but under the result is that under H naught, the test statistic is asymptotically normal with the given 2 complemented for mean and variance, but it appears in the paper. So the next stage of the paper that I saved myself the trouble of looking is a complicated estimator of the 2 complicated mean and variance, which will return to it. But now we are looking again our story, looking under alternatives. So that's the main idea. And the test has non-trivial power if epsilon is very large, because you have H here. I think Q probably are larger than 1, and therefore it's very slow. So that's what I said. You want to be omnidirectional. The price for being omnidirectional is not, you are not omnipotent, you are omnipotent. Basically, you don't have power in any direction. And that is the main conclusion. We'll return to this model in the last slide, I guess, of the talk. How much do we have more? Okay. So if we are talking about so now another look on the co-authors, because co-authors are what really important, I guess. So that's the network. Okay. And we are coming to the bootstrap. And I'll not explain the type. Okay. As we said, the bootstrap is a plugin estimator. You want to estimate parameter of the distribution of statistics Tn under the null, under the truth distribution, and you consider the distribution of Tn under the empirical distribution or any other estimator. But the standard bootstrap, what people usually understand by the term bootstrap, is under the empirical. It works when the law of T given the true distribution is continuous in some neighborhood of N, which is consistent with the empirical. That is, the empirical is close to the true enough to have this continuity of the distribution, and therefore the distribution of T under F can be estimated by plugging in the empirical. The M out of N bootstrap was suggested already in the first paper of Bickel and Friedman, which is almost, I guess, the first real paper about bootstrap. So not the one that suggested the bootstrap, but the ones that analyze the bootstrap. It was mentioned then because problem with situation where Fm doesn't belong to this neighborhood. It's relevant. It's not close enough to the truth for having this continuity, but only we need to have much more precise estimator. So I played it between the two. So usually you look at it in the opposite direction. Fn belong to the relevant neighborhood under M, sample of size M. And the example there, or the typical example, is the maximum of the uniform distribution. And the problem there is that there are anomalies because of ties, for example. So we know that the asymptotic distribution of the maximum is, after normalization, exponential, continuous, but if we'll do bootstrap, it will be very discrete. Okay, this is when we usually talk about sort of confidence interval. The story in testing is completely different because in any or almost non-trivial case, almost all non-trivial cases, Fn is not, doesn't belong to H naught. We want to know the behavior of the estimator under H naught, and the empirical doesn't belong to the null. So I could take many papers that are dealing with this. This is a huge topic in Peter's portfolio. I picked one of them. And the main idea is that we have some statistics that can tell us. We have to look on the distribution under M smaller than N. And if we have the standard asymptotic, the square root of N asymptotics, and we center properly, everything will work. I not enter into the all details, as the translator said. We all know it. We all know them, so we don't have to mention it. And under a few particular trivial, very general structure that there is it's really jack of all trades. The M out of N test work with true power function and continuous alternatives. So it gives you what we want. It is so something is missing in this description, because if we assume that everything is square root of standard square root of n asymptotics, why do we need the bootstrap at all? Where is a problem? And there is another paper that I want to mention by two advisors now, Peter and Yossi Yahav. And this is under the situation where what we try to estimate, we assume that there is a sort of expansion. And now we can look on the M out of N bootstrap, but under different M's. And we can find extrapolate to get the distribution under N. The main focus of the paper is different, is doing it in an optimal way because it saves computation. I didn't mention, just because we are speaking about statistics in the big era. In his first paper, he writes that one of the problem with the Hodges-Lehmann estimator is that the computation is the level of n squared log n, which is almost impossible. Yeah. That's written, you wrote it. Yeah. Okay. So that's the basic idea, and we are coming to the final chapter. Oh, not the final chapter, the current chapter. Sorry. The current chapter. And this is an archive paper. Correlation with Taylor extremal properties. So it started by a work of Surav that tried to find a non-parametric test for bivariate distribution. We have x, y, and we want to basically test whether x and y are independent. So the test is based on takes the x's, orders them, ranks the y's, ranks them, give Ri to the ranks of the y, to be the rank of the yi. If the x and y are independent, of course, R are independent. If they are not, then if Ri is large, we expect Ri plus 1, which is the next, the close to it would be close to it. The next y, the y of the following x would be almost as large. And therefore, we expect this to be a test. So Cn is converting to Cxi, which was suggested by Dete, in fact. And C has a property that it is between 0 and 1. C is 0 only if X is orthogonal to Y, independent of Y. It is 1 if Y is a precise function of X. C is asymmetric in Y and X, so Cxy is not Cy of X. Let's here copy and paste. The G should be, let's say, sort of ignore this line. It is strongly related to the classical symmetric maximal correlation of Rene, which is symmetric, which look on the supermom over all G and H of the correlation between function of X and function of Y. R square is a maximal eigenvalue of the self-adjoint operator, conditional expectation given Y, conditional expectation given X, or vice versa. It's symmetric, it's nice, it has some anomalies. That is, you can make R go to 1 while C go to 0, because just we pick a point. And so it's not much better. It's more, there are reasons to prefer one on the other, but that's theoretical. Took me time to read what I wrote. The problem is that it is Hebrew, תפסת מרובה לא תפסת, and if you have size a lot, you have not size at all, I guess. The efficiency of this model would be 0 under any contiguous alternative. There's the same problem as we saw in the econometrics paper. When you try to be omnidirectional, you get 0 efficiency for any direction. So what can be done? And here the paper returned to idea in 2000 paper, older paper of Peter from 2006, tailor-made test for goodness of fits and semi-perfect hypothesis, which dealt with basically with a same problem with almost same with conclusions, and basically look on the model. We have here, we look on a parametric model. So we look on all class of parametric model like that, which under the null theta equals 0 would give us independence. We create some correlation between the two, but we permit, basically we look on a copula, but so we don't know the transformation of the X and the transformation of Y. We can create the tangent spaces for theta 1, theta 2, etc., do the projection, and eventually we get the projection is all function of X and Y, which has mean 0 conditional expectation under conditional expectation under X0, and conditional expectation under Y equals 0. So we just take any function and we have to normalize it. It's coparallel, so it's under the uniform. It's relatively simple. And we get, for any particular test, we get the log likelihood standard test. So we get this expression. So we now can combine them. And this is this is 0 in expectation only under the null. All of them would be 0 only under the null. So each one of whatever is the true alternative, it would have some power. One of them would have some power. Now we sum them because we have infinite of them. So we have to temper them. That's the title. If you remember the title, the well-tempered jack of all trades. So that's the tempering. And we get a test. We can do it like that. We can do it like Kolmogorov-Smirnov, look on the maximum, whatever. I don't say that this is, and we don't say this is the only way to combine them together, but the basic idea was, and this is in the last, as I said, the last paper of the topic of Peter, or at least the last paper on the topic of Peter that I know about, is the idea of how you can combine test and get something which has power against all alternatives and more power against the more interesting alternatives, and you have to decide what is more interesting. Okay, and to finish the celebration, okay, so I took two approaches to the list of all authors. I now want to what I think should be the right approach, my point of view.
Should all
So
the acquaintance be forgot
forgot
and never brought to mind? Should old acquaintance be forgot and days of auld lang syne? For auld lang syne, my dear, for auld lang syne, we'll take a cup of kindness yet for days of auld lang syne.
one big forest with real of authors about or individuals. Okay, thank you.
We have time for a couple questions, comments.
So I have a question. Thank you, I don't know, you or Peter. What is the role of testing in the big data era when you have millions of observations and thousands of variables?
Okay. First of all, my little experience, and it's little as you know, is that you never have a lot.
The what?
You never have a lot. You always have very little amount of data. Because if you have a lot, a large number of data points, your questions are becoming very precise. You don't collect millions of data points to ask questions which are you can answer by 100. So my personal experience, to give you a new field, I had all calls to a call center of a middle-sized American bank for half a year. And I tried to compute something. And it didn't work. So I did simulation. And the simulation worked fine, so the theory was nice. The problem is that all calls for middle-sized Northeastern bank, American bank, weren't enough to answer the precise question, which is what happened at 10 o'clock in the morning for a typical type of customers. So the same questions exist. Now, my main point, as I said, is why testing is important, because testing, as I said, testing is what. And if I'm looking from this surrounding where we collect experiments, experiments are not linear. We want to move. And this is again the same problem with medical, all this issue of transfer learning. Your sample population is not the general population. And it's very meaningless to ask about estimating parameters because the parameters are not going to generalize. The question whether something works or not, you may hope that it generalizes. Yeah.
Beginning, you said that there was some coherence, some underlying theme, which actually I have to admit are almost all ones which I forgot. What is the common theme that you choose?
Contiguous alternatives and the problem of how to deal with that. I don't know how to deal with contiguous alternatives. And I have to try to be optimal, but I will be optimal only in a few directions. So either I can say that what would be 64, in which directions I'm good, try to combine them. The last the two papers that I mentioned in the last two slides, to combine them in set of different directions. But the thing is, we have non-parametric world out there. We want to be optimal in all directions. We cannot choose. One topic that doesn't fall into this is a bootstrap, and that's the reason I use the apparatchik title, because as much as I could see, you don't care about the test. You don't care about the test. The test is given for you. You try to see how you can handle it. You don't come with the test. You don't suggest tests. You suggest a procedure to find the opinion. Wait.
I'm not going to, I'm not going to elaborate on that.
I think this is a discussion we can continue outside. We'll take a 15-minute break and thank you, Nikki, for a great talk.